So now it's my great pleasure to welcome you to the main event of the night, the Barlow Lecture. So a few words already said about Professor Harold Barlow, so I'll skip that, and I'll introduce our honored Barlow Lecture for this evening, Dr. Michael Cuthbert. So Dr. Cuthbert is the director of the UK's National Quantum Computing Centre, a national initiative that unites academia, industry and government to accelerate the progress in quantum computing. With a background in cryogenics, superconducting materials and solid-state physics, Dr. Cuthbert has been at the forefront of quantum technology for more than 2 decades. Before taking on his current role, he was head of quantum technologies at Oxford Instruments Group, where he held several technical and commercial positions across Japan, North America and UK. He's also Aegis Professor of Quantum Technologies at the University of Bristol, and he serves on several national advisory boards. This evening, Dr. Cuthbert will share insights in the cutting-edge technology programs that he oversees and the exciting opportunities that these open up for science, industry and society. Without further ado, please welcome Michael Cuthbert.
Thank you very much indeed for inviting me to speak this evening. It's an absolute pleasure to be here to tell you a bit about what the National Quantum Computing Centre is doing, but even more so to spend the afternoon actually exploring the fantastic work that was exhibited in all the poster sessions. So my absolute congratulations to those that were recognised for winning prizes, but actually to everybody for putting forward with such enthusiasm all the work that's going on within your department here at UCL. It was really wonderful to to share in that this afternoon. So when Sir Mike invited me to speak this evening, I thought I'd better do my homework before I started and understand a little bit about the history of the department and Professor Barlow, but actually going back a step to Sir John Pender, of whom the Pender Chair was endowed. And Harold Barlow was the 5th Pender Professor of Electrical Engineering, and Sir John Pender, having founded 32 different telegraph companies, was the chair and leading financier of the first successful laying of a transatlantic cable, and went on to establish what became cable and wireless. And by 1866 had demonstrated transatlantic communications, and his cable and wireless eventually were acquired by Vodafone in 2012 for over £1 billion. So right from the early days of engineering, demonstration of engineering and generating value. And the Pender Chair was then endowed to UCL to fund a new electrical engineering laboratory. Having joined UCL in 1884 as a professor of electrical technology, the first of its kind in the UK, Sir John Ambrose Fleming became the first Pender Professor in the establishment of this new laboratory. And it's interesting to note that Fleming was one of the last students to attend lectures in Cambridge by James Clerk Maxwell in person before his untimely death in the 1870s. He went on to work with Marconi to demonstrate transatlantic radio communications, and then whilst working with Marconi in the early 1900s, invented the thermionic valve, which not only revolutionized what would become electronics, as we can think of it, you could also say it absolutely transformed culture within the 20th century. So from communications, radio, to radar and telephony, but then also think of radio, television, sound recording, sound reproduction, so really changing the way that electronics became part of our lives. And indeed, the early days of computing, which we'll talk more of in a moment. following very early work in the Royal Naval Communications on radio, Harold Barlow first came to UCL in 1919 as an undergraduate, where he took a 2-year course in what seemed only about 15 months and graduated with a first-class honours. The following year, he remained at UCL as a student under Fleming and was awarded a PhD in science because there was no such degree in engineering back in those days. He joined UCL as a member of the teaching staff, focusing on power generation and transmission, but then was asked and tasked to think about how we could bring electronics and telecommunications to the department as a new subject and how that could be taught to undergraduate students. And during the Second World War, Barlow was recruited into work on radar with a number of other academics from around the UK. And on his return to UCL in 1945, he found the department almost completely destroyed, and with only 4 academic staff at the time, needed to really rebuild not just the bricks and mortar, but actually the whole fabric of the department. And in his post-war career, as we've already heard, he spent most of his time thinking about microwave, long-range microwave telecommunications. But throughout his career, he actually moved up in frequency as he thought about some of the theoretical requirements for those long-range communications. And in a nod to early innovative thinking, he was awarded a grant from the post office at one point to work with BT at Martlesham to establish a test bed, the first of its kind, thinking about long-range communications and the potential of what sort of technologies would be needed to actually drive that application. But his ambition for long-range communications using microwaves, as we've already heard, was superseded with the advent of fiber optics. But not deterred to have seen 20 years of his research not come to the fruition that he'd hoped for, he actually pivoted to thinking about how could we make coaxial cables much more efficient and understanding the theory of fiber optics and the rollout of fiber optics as the communication tool that is used so widespread now. So from cable and wireless and the sub-Atlantic cables for communications all the way through to the foundations of the internet, Barlow, I think, has a rather unique position in connecting those pioneers from the late 19th century all the way through to pioneers today in the 21st century. So to the 21st century, so quantum advantage is where I wanted to start, and to think about what is it that we need to work through in terms of a roadmap to understand the technology and its impact. So if we assert that there's a class of problems quantum computers can efficiently outperform their classical counterparts, we need to answer 2 questions in terms of actually demonstrating quantum advantage. So, does such a class of problems exist at all? And if it does, can we engineer a machine capable of doing that sort of computation? So I chose the 13-digit number, but you could choose any number. So square root of a very large number. It's a trivial example, but it's solvable. But it requires some kind of algorithmic approach. So you have to seed the calculation, calculate how close you are to the answer, and form some kind of iterative approach. If I gave you a different number and asked you to calculate 1, 2, 3, 4, 5, 6, 7 squared, you could do that exactly, and you could do it directly. And so in this kind of trivial example, we can demonstrate that the cost of the solution and the cost of verifying the solution is not the same. Now, for arithmetic examples such as this, we typically don't worry about it because we can do it on our mobile phone, we can do it in our pocket calculator. But for very large, complex calculations, we do need to think about the difference between how we perform calculations in polynomial time, as it's described, and the cost of actually verifying the solution versus generating the solution in the first place. And there's an open question around these different classes of problem and whether the solution can be as quickly verified by a computer as it can also be quickly solved by a computer. So there is another class of problems that have been defined, which are so-called bounded error quantum polynomial time problems. And that is based on the assumption that there is a set of problems that is larger than polynomial problems that are solvable with a quantum computer in an efficient way that goes beyond the scope of a classical machine. And if that is true, then it makes sense to build a quantum computer. But this is an open question in information theory, and so it's not a given that, as drawn, these are discrete sets and subsets. It's not known that this is the case. So we can perhaps think more generally about what is it that classical compute is really good for versus what might a quantum computer be best targeted towards. And for example, number crunching and big data. We will not do better than CPUs and GPUs in classical compute for large data sets with a quantum computer. Quantum computers are best suited for problems where there's a large parameter space and or sparse data sets. So where we have a data set that has holes in it. So actually finding where the pattern from the noise is the type of problem that quantum computers are better suited toward. In a quantum computer, so we harness quantum mechanics. We use the properties of superposition and entanglement such that the qubits can hold and manipulate information, and that is greater than their classical counterparts. And then through a process of interference within those entangled quantum states, many possible outcomes are cancelled through the interference process, and others are amplified, and that amplified outcome becomes the solution from your quantum computation. So how does that compare if we think about the scale of machine that we're talking about? Well, and there's a bit of a false equivalence here because this is the size of machine you would need to simulate the number of qubits rather than necessarily the power of that number of qubits. But regardless, the memory you have on your mobile phone would be enough to simulate 20 qubits. When you get up to 48 qubits, that's an exascale supercompute level of capacity that you would need to actually simulate the states within 48 perfect qubits. 165 qubits, you would need every atom on Earth to build a computer to actually simulate the number of states within 165 qubits. And by the time you get to 267 qubits, your computer is now the size of the observable universe and would take the lifetime of the universe to run. So we've got some sense that there are a set of problems we want to solve. We've got some sense of the power of a quantum computer. And are we suitably motivated by meaningful problems to solve? And typically, quantum computers and the type of problems that they lend themselves towards fall into four different categories. One in cryptography, which I won't say anything about this evening. Simulation, machine learning, and optimization type of problems. And these crop up in all industries, in all walks of life, in all aspects of science as well. So, for example, lowering energy costs and greenhouse gas emissions through the simulation of chemical processes, such as nitrogen fixation in fertilizer production. Optimization of cargo loading, reducing fuel consumption in routing and logistics. And there's a piece of work that the NQCC did with Unisys, where we were able to show that just a 75 centimeter imbalance on the center of mass on a cargo flight costs 4,000 kilograms of fuel extra on a long-haul flight. So if you think of how much cargo is routed around the world, these sorts of small increments really start to add up, something that quantum computing could lend itself very favorably to the economy and to society. Machine learning for anomaly detection, so in financial services for detecting fraud, for example. And you can see some numbers there that over the last 8 years, fraud in the UK in the private sector has grown by more than a factor of 10 to £157 billion per year. The same approach for anomaly detection can be taken in medical imaging. In 2018, so 215,000 cancer cases were diagnosed, and almost half were at stage 3 and 4. So if we had some technology, and there's already a significant program in using AI to look at medical scans such that we can improve our early detection and identification of the right treatment for patients. And of course, the driver here is the earlier the detection, the better the patient outcome. And then the other one that I'll raise is simulation of proteomic biomarkers in neurodegenerative diseases. So again, these are very complex chemical, structural problems, but the impact on society in a very large way. Over 1 million people are living in Britain with neurodegenerative diseases. We have partial treatments, but we have none that lead to reversal of symptoms. We can slow it down, but we can't reverse it. We need to understand these chemical processes within the brain in a much stronger way. And there's already a clinical trials unit with the Medical Research Council here at UCL that are working on exactly this type of problem. So we've perhaps convinced ourselves there's a set of problems to be solved. We're suitably motivated that society benefits by solving them. What do we need to do some engineering and build a machine? Well, this was laid out by David DiVincenzo in the mid-90s when he was working at IBM. And he said, well, there was 5 things you need. A scalable system with well-characterized qubits. And I would ask, well, are they well-defined? Are they stable? Are they controllable? A simple 2-level system is not good enough. Can you make them? Can you make lots and lots of them? Because we're going to need millions of qubits in this quantum computer. You need to be able to initialize the qubits. So can you set and reset to a specific state? Can you do it reliably and reproducibly? And can you do it quickly? And that's absolutely critical within the life of your calculation. And indeed, our prize winner of the poster was working on exactly this topic of how can you run these initialization and reset responses very rapidly. Do you have long and relevant coherent times? So how long does your qubit, how long does these quantum states need to survive? And what is the meaningful length of time that it survives such that you can run quantum operations within that coherence time without any degradation on error rates or noise level? You need a universal set of quantum gates, so that means in principle you must be able to entangle your qubits, so from one qubit to the other. And you need to be able to measure your qubits and the state that they're in. Is it accurate? Is it selective? Is it repeatable? And given that it's a probabilistic process, how many measurements do you need to do to satisfy your algorithmic integrity? Because that all feeds into how fast is your processor and how long does your computation take. So those criteria in what we actually need to build a machine set out a number of challenges for us. So on the technical side, what is it that we're going to need to actually make a machine? Well, qubit scale, we need at least 1 million. And there's many papers out there that would argue you need tens, hundreds, or perhaps billions of qubits to do any kind of meaningful calculation. You need long coherence times, and certainly you need at least 10 to the 5 gates per coherence time. I would argue you actually need much more than that, but perhaps for modest scale machines today, that's a good target. You need error rates that are very much less than 1 in 10 to the 4. Typical error rates available commercially on scalable platforms are 1 in 10 to the 3 currently, and we're pushing towards 1 in 10 to the 4. You need gate speeds of less than 50 nanoseconds, so these need to be fast processes. There are some of the qubit candidates that actually run more typically with kind of 1 millisecond gate speeds currently. I can't see anybody investing in a technology of the future with a 1 kilohertz clock speed. So that's something that we absolutely need to have, these rapid gate speeds. We need a circuit depth of about 10 to the 9, so how large a computation can you run across the entirety of your qubit layer. An architectural overhead, well this speaks to the error rates. How many qubits do you need to run your error correction process given your computation qubit? Early estimates 15 years ago would have been something like 10,000 to 1. So for your 100 million qubits, you're using 10,000 for every calculation qubit just to keep that qubit alive. Those estimations on resource are coming down all the time with ever more sophisticated error correction schemes, but nevertheless the overhead will still be tens or perhaps around 100 to 1. Signal readout, we need it certainly better than 1 in 1,000 error rates. And we need distributed entanglement. We actually need to go within chip, from chip to chip, and then from module to module as you build out a future quantum data center, if one can imagine what that could look like. We need real-time error correction. That's a latency problem. So how do we actually have error correction and data comms from module to module, chip to chip, and on chip? And to get to anywhere where we can start to do some really interesting calculations, and the likes that I kind of showed the motivation for, those big societal challenges, we need something of the order of 1 trillion coherent operations within that calculation. So the technical side seems pretty daunting, but there are some practical issues as well that we need to think about. The UK government published National Quantum Strategy in March of 2023, and it talks about the contribution that the quantum computing and the quantum sector will make to the UK economy in a decade's time. And it's anticipated that the contribution to gross domestic product will be something of similar to the pharmaceutical industry is now. The pharmaceutical industry, over 20 billion GDP, employs 65,000 people across the UK. So if we're going to have a quantum industry in a decade's time that's comparable, it's at least going to have to employ 30,000 people. in a highly skilled, highly technical industry. At the moment, between the startups and the research community, we have maybe 10% of that 30,000. And as fast as you're pursuing your PhD, and in physics, and of course universities across the country, people are pursuing their PhDs, it isn't going to be populated just with quantum physicists. We need electrical engineers, but we need technicians, we need apprentices, we need people who are already working in the telecom sector or in other technical industries, in computing science in particular, that actually will come into quantum computing to build this workforce that we need for the future. The cost, current cloud services are about $100 a minute. I would argue that needs to be at least reduced by a factor of 100, $1 a minute. $1 a minute would still not be competitive with AI. So if quantum is going to be competitive, it has to seriously outperform or be competitive from a price point. Size. Well, I don't know the answer to that one. There is an argument that a large-scale quantum computer could look like CERN or Diamond Light Source, or a very large international and national facility. My view is if that's the case, we've picked the wrong technology, and that we actually need to think about what's the right paradigm to bring the size and scale of these machines down. Something that's the size of 25 rugby pitches with a power station sitting on the side of it doesn't feel like the right answer, regardless of the physics. We need a really seamless workflow. Our end users of the future will not care if it's a quantum processor, classical processor, GPU, neuromorphic. They want their problem solved. They don't care how it's solved. And so that has to be a seamless process into existing classical workflows. It needs to be secure, so we'll have to have post-quantum cryptography embedded within it. We need to grow the user base. So we're not running against a static classical compute landscape. AI and classical machine learning has been developing at an incredible pace in recent times. And quantum computing and the quantum computing sector has perhaps rather looked over at classical compute as a fixed entity. That's really not the case. And so we have to ensure that we are developing users as fast as AI has been over the last 2 years, certainly. Compelling use cases. So I described some of the use cases at the beginning, but we really need to have verifiable quantum advantage. That's what will keep investors engaged, and that's what will keep governments engaged in demonstrating that there truly are a set of problems that you cannot do classically, and that a quantum computer is an inevitable tool that we need to employ for those sorts of operations. The industry needs client capture. So by that, I mean, how do we get the big corporate end users to pivot from R&D teams exploring new technologies, thinking this is all very interesting, let's see what it can do, small technology sprint projects. How can we get them to pivot such that quantum computing becomes embedded operationally within the delivery of their business, whatever that industry sector is? And then fundamentally, the quantum industry needs revenue to start outstripping R&D spend, like every other industry that provides products and services. At the moment, that's very much the other way around. And so we're relying on patient capital and governments to provide the R&D spend for that kind of endeavor. So I wanted to take you through 4 areas that the National Quantum Computing Centre is trying to support these pieces of work. So we were formed 5 years ago, a new national laboratory at the Harwell campus, a collaborative program between EPSRC and STFC. Initial investment of £93 million. About half was for a new building. a quarter of the equipment to go into the new building, and the other quarter was the 5-year program to hire our staff, run collaborations, and build out our program. We've benefited from subsequent acceleration investment, and I'll say more about that in a moment. And our core purpose is to examine the challenge of scaling quantum computing, both the technology and the user community. We've had 4 main themes: technology, infrastructure, applications, and skills. And our watchword has been collaboration. So we can't do it all ourselves, and in fact, we are there to try and support and catalyze the wider community. And within technology, so we have over 20 collaborations on hardware, software, and control systems across superconducting, cold atoms, trapped ion, qubit modalities. We have 25 different projects with 41 industry players on application and use case development. And a very major collaboration with the University of Edinburgh and the School of Informatics, thinking more about some of the theoretical aspects of quantum computing and benchmarking and verification. On skills, we've done a lot of work in this area because you don't need a building for those parts. So actually a lot of that program started very early, before the laboratories were up and running. We've nearly 6,000 public engagements now over the last 5 years. 600 online courses have been delivered with Q-Control, who we've been partnering with. Over 150 hackathon delegates. 60 continuous professional course delivery through our partners at the University of Bristol. 9 PhD sponsorship students so far, and 3 early career fellowships in partnership with EPSRC. So we've been really trying to support that, build that ecosystem for the longer term. So let's take each of these 4 points one by one. So scaling the qubits. Well, there are lots of different modalities, and they're usually described as either synthetic qubits or natural qubits. I would have a bit of a contention about the natural qubits. Yes, indeed, the ions or the atoms or the photons are all identical. But the nanofabrication needed to contain them, to get the signals in and out of the devices, or the optics required to trap them, still requires a level of intervention in engineering that means the atoms might all be the same, but actually, are we creating an environment that is identical for each of those atoms? And we know that we're not, because we have noise sources. So that's something that I think I would argue that all of these are synthetic qubits, because actually they need nanofabrication to contain and make the devices in the first place. And each one has merits, demerits in terms of the qubit performance and that list of technical requirements I showed you earlier. And that means they have different scaling approaches and strategies, thinking about how do we actually build out not a few qubits, but a very large number. Photonics and semiconducting qubits typically are thinking about how do we get from small arrays of qubits very quickly to build very large numbers on large-scale wafers. The trapped ion topological community, perhaps more typical, looking at how do we get the error rates down as low as possible, and then think about scaling once we have those very good qubits with very low error rates. And the superconducting community are perhaps working more in the middle of saying, well, how do we step by step make continuous improvement on both scaling and error rates and numbers of coherent operations. And then thinking about monolithic chipsets versus network chipsets. So on the bottom axis here is the ability to scale out, so the ability to add more modules, and the axis on the left-hand side is the ability to actually make large-scale chips, monolithic chips in the first place. And you can see for the semiconducting ones in the top left, we know how to make millions of transistors billions of transistors in conventional electronics. So we know how to pursue that type of system, and we also know that the other modalities lend themselves to nodes or modules that can be built out. One of the key challenges, how do you communicate at the right frequency between those modules? For superconducting devices, that means we need to be able to transduce signals from microwaves on chip to optical off chip and back to microwave on the next chip. And that's a real challenge in thinking about how one could scale that out if we need to actually have multiple chips across multiple platforms. For trapped ions, typically they're running they would be communicating entanglement through blue light. And that means that you have heavy losses within fiber optics, and so perhaps don't lend themselves to large-scale networking. Whereas some photonic chips and semiconducting systems already working very close to telecoms frequencies, the infrastructure of communicating light within a data center is already well established and can build on conventional technologies. I would say that there is still room for new modalities to break into this. I don't think it's a given that the ones we have today are the only ones possible, and there are new qubit types being proposed all the time. And this, just to highlight, is a really beautiful piece of work from Andrea Morello's group at University of New South Wales, where they have a multi-layer or multi-level qubit rather than the qubit. And so with 4 qubits, have the equivalence of 16 qubits, and so actually could scale through ever more sophisticated control signals rather than ever more complex devices. And that opens up a very large dimensional Hilbert space in terms of driving those calculations. If I move on to think about the signal I/O and readout, so one of the things that we've been doing at the NQCC is thinking, the picture on the right-hand side here is from IBM, where you can see that the qubits are hidden in here, but almost everything else on that picture is the mechanism to get the RF signals in and out of the qubit layer. So we've been working with Rigetti and Seek, and I did note that some of you are also working with Seek here at UCL in thinking about how we can really drive simplification of that I/O system and the signal conditioning. Can we improve readout fidelity? Reduce the component count, so get rid of all of these attenuators and signals and coaxial cables. Release fridge space at millikelvin so we could actually get more qubits in there instead of more amplifiers and attenuators. And then could we start to enable real-time error correction for superconducting devices where currently the readout is not yet good enough? And of course, for Professor Barlow and his work on coaxial cables, whilst it's been an absolute mainstay of this brute force approach for quantum computing and superconducting and semiconducting devices, I'm afraid we are doing everything we can to get rid of it because fundamentally it's not going to be sustainable to build out machines that look like this in the large scale, both in terms of the complexity of the engineering, the reliability of the components, and the cost. These sort of machines, for a typical 50 to 75 qubits, it's about £1 million for the dilution fridge. It's £5 million for the coax cables, and about £5 million for the room temperature electronics, before you have paid anybody to develop the technology or to deliver that technology as a service. So just the components. It's not a sustainable approach. Many of you will be familiar with this type of picture of free space optics. As a non-optics person, I find these sort of pictures absolutely mesmerizing. I think, how on earth does anybody know where these optical path lasers are headed on top of the table. And we've been thinking within the NQCC about modular laser delivery and in-fiber light delivery, such that we could move all of this optical components that's on the optical table. How can we move that into rack-mounted modules that become engineered, repeatable, scalable, flexible, and have laser safety built into them, rather than have staff in the lab with free space optics needing to wear eye protection. And so we've been working with STFC Mechanical Engineering Department to think about how we can actually prototype some of these machines, where we start to take the weight, for example, has been reduced by a factor of 6, the footprint needed for the free space optics by a factor of 4, the degrees of freedom for aligning all of those components reduced by a factor of 3, and the component count by a factor of 2, which cascades through to cost. So this is not anywhere close yet to the kind of productization of the technology, but it does mean the role of a national lab. We can actually take some of these technologies, make it much more modular, and feed that back into the research community such that it benefits everybody. And so I'm sure Barlow would be delighted to see that we love fiber optics as much as we want to get rid of the coax cables. Moving on to think about use cases and client capture, we've been running a program called Spark for the last 4 years. And that's really reaching out to industry sectors to think about what sort of access is needed to real cloud services, what expertise, technical support can we provide them so they can actually start to write real code on real life problems. How do we bring best practices together across different sectors that might ordinarily not speak to each other? And then how can we support the skills agenda within industry where you already have computer literate, highly skilled people who we are bringing into quantum perhaps a bit later in their careers. And added to that, we've been running a user program initially targeted for academic research community to provide, as a facility, to provide access to cloud services for quantum compute resource for research purposes. We've now run a quarterly call for proposals for the last 2 quarters. We've had around 20 in each of those calls, and that's something I'd certainly encourage those who are interested in exploring how quantum computing might become a new tool for their research purpose, that we're able to support that type of work. And then the other thing that we've been doing, and this has been a huge piece of work that we've been collaborating with Innovate UK to deliver, is thinking about this testbed initiative. So how can we provide confidence into the quantum computing ecosystem in the UK such that there are the beginnings of government contracts that actually start to create revenue rather than grant funding. And anecdotally, investors tell us they prefer a government contract, real revenue, by they can leverage 3 to 1 in terms of investment compared to grant-funded R&D. So we put out an expression of interest. I say we've been working with Innovate UK on this with £30 million SBRI funding call. So this is a kind of pre-procurement round of investment. 7 commercial systems, 5 different modalities. We're not yet picking the winner. And those projects initiated in January 2024. They ran for 15 months with a 3-month extension. And we've now got 5 of the 7 systems deployed at Harwell, with 2 more that will be coming over the next 6 weeks or so. And 2 of those 5 are already outperforming their R&D counterparts at their commercial headquarters. We're in commercial negotiation to have follow-on contracts beyond just this first stage. And we're working very closely with the University of Edinburgh and thinking about the test and evaluation of those systems. In the end, the test and evaluation is the thing we really want to get to. How do we understand how these work, how they perform? Can we benchmark them? Do we understand what we could do with those systems? And so we have a 2-year program that's been scoped out in terms of thinking about the verification and benchmarking. And that's built on a very extensive piece of work we commissioned in partnership with NPL, which is, there's an archive paper that was published a few months ago, Lal et al., which actually brings together all of the device level, the system level, and the algorithmic level verification techniques across the different modalities and actually puts it in one place that has allowed us to build this program of benchmarking for the future. We're not alone in running these type of initiatives, and so this is just one I put side by side, the DARPA Quantum Benchmarking Initiative in the US. With a much more modest budget, we feel that we've actually been able to go in a very agile way, at pace, to be able to create on-premises hardware delivery to support those startups, and ensure that the startups retain their own intellectual property. They are best placed to exploit it, and we think that's really important that they retain that. What we have not done, that DARPA are doing, is audit the supply chain and looking at the component level, and that's something that potentially we could collaborate with our colleagues in the US. So I think the final thing I wanted to just quickly touch on in the remaining few minutes was, what does the UK roadmap look like for what is a very complex problem with many moving parts? And I mentioned the National Quantum Strategy, which was launched in March of 2023. This was followed up quite quickly with 5 quantum missions that were defined. This is not government policy, but as Sir Peter Knight said the other day, if you say it often enough, maybe it'll just become government policy. This is not yet funded, but within mission 1 on quantum computing, we have 5 themes around hardware, software, user access, applications, and the underpinning science to deliver what is a very ambitious target of getting to 1 trillion coherent operations within a decade. The roadmap here, which is perhaps a little bit difficult to read in detail, but the takeaway message is we need to improve performance by a factor of 10 per year for a decade in order to get to this 1 trillion coherent operations scale of machine. That's quite a daunting task. And there are lots of other roadmaps that have been put out, and there's just a selection of various commercial roadmaps, and they all say a very similar thing, which is over the next decade, the industry is moving collectively towards that type of scale of machine. There are other roadmaps actually looking at specific applications, domain space. This is one that the NQCC we've worked on with healthcare and pharma to understand what's the roadmap. As the technology becomes available, what can we do with it, in particular in the healthcare and pharma sector. So, is that going to be enough? Well, this is the plot that was created in 2003 by Steen, updated by David Lucas in 2020, that showed with the data points there, you can see in the red and blue for superconducting, red for trapped ion systems. In 2020, we were barely on the landscape, never mind starting to climb the mountain. Updating, again, red for trapped ions, blue for superconducting to 2024. Well, we're starting to move into the foothills, but to be honest, we're still not at the scale of being able to do any kind of viable computation. The 5-year goal of that ambitious mission would take us to the edge of the yellow line, and in a decade, we get to the green line. So we're still at the bottom of the mountain in terms of climbing, in terms of the type of computations that we'd like to be able to run. The DARPA program actually brought together resource estimation from across a variety of different sources. And if you then try to take their data plot on the bottom left-hand corner and say, well, where does that sit on our map, on our mountain? Well, it's encouraging, but it still feels just about out of reach. So we also need to be working on algorithm development such that we can push those valuable applications down the mountain rather than just assume the only way is to make ever more sophisticated hardware that takes us up the computational mountain. Oops. So if I come back to our two questions around quantum advantage, does the class of problems exist? Well, I think we can probably convince ourselves that actually there's really well-framed questions, and we're well motivated for societal and economic benefit to tackle them. Can we engineer a machine of the size capable? For me, that's still a bit of a question mark. We will certainly be able to engineer highly valuable computational devices. Whether we get to a full fault-tolerant general-purpose machine, I think there's still a question mark, and certainly in the time scale of such an engineering endeavor. I'll leave you with just some kind of final thoughts around where will this roadmap take us? Well, on hardware, I can be pretty confident we all need photonics within the architecture of whatever is built. There is duplication happening right across the industry, the ecosystem, the research community, and so we need to start designing to stack interfaces instead of thinking that each company can only survive and can only make its investor pitch if it's full stack, because they will be working on software layers and error correction that look almost identical to the next startup and the next startup and the next startup. Certainly in the UK, we haven't got enough skilled people to continue to do that. So we need to start working of designing the interface. My view is the control architecture is going to take significantly more work to scale up than the qubit layer. If you think of all those interfaces and the I/O structure, and we have to do much better on energy consumption. We cannot build a new computational system that relies on high-performance compute and adds to the energy challenge that the computing industry already has. On applications, for sure, there's going to be some really interesting science use cases before some of the commercial use cases. I think healthcare and crypto will keep governments engaged. We're going to need much more than 10 to the 12 or a trillion coherent operations. And for sure, there's going to be new science along the way. I'm fairly convinced, in terms of value, there's going to be more than one qubit winner. It is in the interest of all the startups to say that their qubit type will be the winner. Of course it is, but I think there's room for more than one. Single-purpose machines will have their day, certainly for key applications before we move to general-purpose machines. That will take longer than any of us would like, and I suspect regulatory anxieties will slow us down, as will geopolitics. So I'm going to finish at that point. Thank you again for the invitation to speak tonight, and just leave you with an advert for our hackathon that's happening later this summer for anybody who'd like to get hands-on, real-world problems with real cloud service machines. You have about a week to sign up for the hackathon that's going to be in Edinburgh later this year. Thank you.
Thank you very much, Michael, for such an insightful talk. We now have time for a few questions from the audience. Is there a first question ready? If not, I can start. Michael, so AI, you identify them as some competing technology that quantum technologies quantum computing has to overcome. Is there also opportunities for AI to inform how to scale quantum computing better?
Absolutely. So I think that there's two elements to that. How should we harness AI, for example, for the recalibration of large-scale control architectures? So that would be one area where AI could inform the technology. I think quantum, rather than thinking of how will it compete with AI, which of course it will for users, but actually quantum can turbocharge AI as a use case in of itself. So certainly computation where you have to seed the answer, quantum may be able to seed the answer significantly faster than conventional techniques, and then the number crunching can happen after that with classical machines. And that kind of hybrid approach is something that IBM, D-Wave, and others are increasingly beginning to embrace, recognizing that the workflow is not one or the other. It will be both.
Thank you. Michael.
Quantum physics, you know, is full of surprises. So do you think actually that the mechanisms of quantum physics which are now being developed basically can actually produce the quantum computer? Or do you think there is still room for new effects, new concepts yet to be discovered, which will offer advantages?
So I have no doubt there'll be new physics to be discovered along the way. Absolutely. Whether that will inform our engineering, I don't know. I suspect that it will. I get very frustrated when I hear people joining the quantum computing hype cycle in saying the physics is done, it's just engineering. First of all, it feels a bit derogatory for a start, but I don't believe that for a second. I think the physics, and certainly some of the information theory, still needs to be evolved to really inform what the engineering will be needed.
Neil.
Hi. Very nice talk. If you look at the fields of, say, astronomy or high-energy physics, there came a point where the fields really coalesced so that there are massive cross-the-board research rather than, and I think you did make reference to this, but rather than just siloing of lots of small institutions and countries even working on different problems or maybe the same problem again and again. Do you see any possibility that the quantum computing community might eventually move more to that sort of approach?
So, I mean, what I've observed, when the technology would be described as pre-competitive, there was a real appetite for people to collaborate. I think even though the technology remains pretty much pre-competitive, in reality, the pursuit of investment and capturing skills is highly competitive. And so perhaps there's a reluctance for some parties to work together. There has been signs of a kind of quantum protectionism from some countries, which has certainly inhibited industry players and governments working together, perhaps less so for academic research. And given quantum computing is a dual-use technology, I would expect that that is a reality of life, and the export controls and things are just things that we need to find our way to navigate through, rather than try and pretend they're not there, or indeed try and remove them. I see with all the roadmaps that are getting published that I mentioned, I see an absence of how rather than what. Now, that's probably bound up in companies' intellectual property, but it's when people start to expose the how, then I think you can get really good collaborations where consortia come together and work on a problem that can then be disseminated to the benefit of all. I don't think the community is there yet. There are some open source programs, particularly around control architectures and error correction. It would be nice to see some more of that develop. And even as a national lab, we're still figuring out whether we should be open source or actually should we be generating value within UKRI such that there is a commercial return in some way rather than necessarily just immediate benefit to the UK economy. So we're still working that out as much as the commercial players are.
Alvin?
You first.
Sorry. Hi. My background is in financial services, so I'm not a scientist at all. The first few slides you mentioned that the equivalent of 256 qubits can power the universe or creates the universe. So why is it that we need millions of qubits to solve problems that seem smaller than the creation of the universe?
So that's where I said it was a kind of false equivalence. Indeed, you're absolutely right. So if you were doing a classical simulation of 267 qubits, you would need a classical computer the size of the known universe. If you want to do a quantum computation and run the statistics of the computation with the right speed, with the circuit depth, such that you can simulate chemistry or some of the other applications I talked about, that's where you need a machine that is millions of qubits. So then it becomes a kind of nonsense problem to say, well, you would need millions of universes in order to simulate your millions of qubits. It's only a measure of how classical compute suddenly gets outstripped by the power of quantum and actually gets outstripped very, very quickly. But that doesn't mean once we've outstripped classical compute, we can actually do the types of computations we really want to explore.
Thank you. You said you wouldn't say much about crypto, but I just wanted to ask, within the crypto community, the development of post-quantum algorithms, do you think that, in fact, that is at a pace at which there will no longer be a huge crypto application for quantum computing? How do you think the competition is going, I suppose is the question.
So I think there will always be a need in the crypto community to use whatever is the state-of-the-art quantum computation to actually scrutinize that post-quantum cryptography to see if it's genuinely post-quantum or will be outstripped at some point or by a new protocol. I think it's true to say with most classical encryption, there's needed to be upgrades and patches over time because new methods have come out to actually defeat what was once at one point in time seen as undefeatable. So I think that will be an ongoing synergy between the crypto community and the quantum computing community as the technology develops. So if there's suddenly the onset of error correction, for example, something will happen in the technology space that means the crypto world will have to rethink. Now an adversary might have a fully error-corrected machine of whatever scale. So I think that will be kind of symbiotic for the future.
Hello, down here.
Oh, hello. Sorry, you're behind the screen there.
Yeah. So you answered your initial question, said yes, there is a class of problems for which quantum computing will be a good application, will be necessary, and gave it a green tick.
Yeah.
And I'm just wondering about the algorithms and how the general framework for creating algorithms for those problems. And I apologize, I don't have a lot of knowledge about creation of algorithms for quantum computers, but I understand there's a lot of subtlety in terms of getting the correct solution to be spat out. And I was wondering, is there a framework that when we have those problems and we have a general purpose quantum computer that we feel we can create algorithms for all those, or is it really going to be a new research project for each one?
So there's a whole suite of algorithms that have already been developed. And in fact, the kind of computing science theory side of quantum computing is well in advance of the hardware and the engineering to some extent, because actually some of the techniques I talked about are relatively recent, whereas the theory has been in development since the 90s. Certainly, so the likes of Shor's algorithm, Grover's algorithm, the kind of more well-known ones. So there's a whole suite of algorithms already available. It is not yet, I would say, a kind of pick and mix where you just go into your drop-down menu and decide which algorithm I want for which type of problem. Algorithms are still being developed, and that's true of classical compute as well. But it doesn't need a brand new algorithm for a brand new problem. I think the mathematics for most of these, the problem types within these classes of problem types, as I mentioned, the mathematics is well understood, is well developed. It is about finding ever more efficient ways of running an algorithm given the architecture or given the noise profile or the error correction of that particular architecture. One of the things that the computer scientists are really like at the moment about how they can think about these architectures is that they can address each individual qubit one by one, and they know which one they're addressing, and they know which one is noisy, and which one has good coupling to its next nearest neighbor, and which one has lousy coupling. When you have tens of qubits, you can actually start to write your code to account for that. When you have 100,000 qubits, there's no way that you can start to think about that. You have to think about the qubits as a kind of amorphous group. So I think there will be a pivot in algorithm development, which will move from understanding qubits on an individual basis to actually understanding qubits as a network or a structure.
Yeah, and if I just quick follow-up on that. Yeah. So does that mean you could now teach a course on quantum software development? I guess I'm just saying Shor's algorithm and Grover's algorithm always get referenced, and there might be quite a few others, but it's not so much that there's a set of algorithms, but there's a general framework. You could teach a course, which means people now know how to create algorithms for any new problem that you come up with.
Indeed, you could, and there are lots of other algorithms, particularly variational techniques that one could point to. It tends to be, you're right, Shor and Grover are the ones that get mentioned, but there are lots of other techniques.
Excellent, thank you.
We have time for a couple more questions.
Thanks. I was just wondering, I know sort of in years gone by, there might have been quantum winters where interest and funding has kind of waned in the area. Do you think that the momentum is such now that, quantum is just going to continue to improve and improve up to the, million qubit limit? Or, is the kind of relentless improvement in classical computing going to kind of render quantum to the dustbin of history, like the HO1 waveguide?
So I think no matter how good classical compute becomes and continues to develop. The reasoning I showed at the very beginning doesn't go away, that no matter how good a classical machine is, it is bounded in terms of the scale of computation, the types of problems that it could be approached. Again, well-known problem, the traveling salesperson problem. So it's really a cost function on resources. So how many cities do you want to go to, and so forth. With 22 variables, a classical machine would take the lifetime of the universe to solve it exactly. So we use approximate methods. Those won't go away because at the moment they're good enough and they're quite inexpensive. I think the question of a quantum winter has come up very frequently over the last 5 years, and so far there's been no real sign of any indication of a quantum winter. What I believe will happen, and this is a normal function of new nascent markets, there will be a period of mergers and acquisitions, so there'll be some consolidation within the quantum sector. That might mean companies go out of business or pivot and move on to different technologies. That's fine. I think for the UK, the danger is that some of our really innovative startups look quite cheap if a large corporate decided to come and acquire them. And so I think that's something in terms of us building out a UK capability and maintaining our intellectual property and so forth, that we've been ahead of the game. So we actually need to double down on staying ahead of the game within that quantum sector rather than allow some of those real innovators to get bought out. But I see that consolidation is inevitable, but I don't see a quantum winter as such.
One final question? Well, I think this... Oh, we have Dominic. Oh. Thank you, Dominic.
Just squeeze one quick one in the end. I think with all technologies, it's interesting to have our eye on, is there an up and coming, just as was mentioned before about the HO1 and then along came fiber optics. It's interesting to have our eye on, is there another way of solving this problem? Will anything come along? Is there anything within the fundamental physics that you're aware of that says that this is the only way to solve these kinds of problems? Or could something come along to kind of subvert the dominance of quantum computing?
So I'm not aware of anything that would completely subvert quantum computing. I think there are exploratory ideas and things like neuromorphic computing that could be disruptive. Not least, it could actually start to pull some of the talent away from quantum computing into something else that's interesting and new and is so interwoven with brain science and thinking about the neurology of how we operate. I think there could be other disruptive aspects, particularly around energy, and that if there's a technology that's good enough that could offer good enough performance at 1,000 times less energy consumption, I think those sorts of technologies could start to win out. But I'm not aware of anything that would completely subvert quantum computing at this point.
Okay, so this brings us to the close of the Q&A. And please join me in thanking Michael again.